Hello, and welcome to the Fantasy Football Draft Assistant Launch Report. My name is Thomas Kiefer, and I am in a team with Caleb Miller, Hashim Afsal, and David Blankenship. For the introduction of our project, we have to talk about fantasy football, which has exploded in popularity over the last 25 years in the United States. 30 million players play fantasy football in the US alone every single year, and it consistently generates over $10 billion every NFL season. Fantasy football is part of the growing machine of sports gambling in the United States, which is currently legal in 39 states and will likely be legal in more soon. And over $120 billion was spent on sports gambling in 2024. The effects of this increased popularity and lucrativeness has created a diehard community of amateur fantasy football managers, and everyone is looking for new ways to gain a competitive advantage, and that's where we come in. So just to recap where our project currently sits at, in DSci 591, we built a really robust data set by scraping and merging golden standard professional football data sources, so things like ProReference and NFL.com, and we engineered a ton of meaningful features and then mitigated their multicollinearity to acceptable levels where we can use them. And we did this by growing very familiar with the data through EDA. Now we'd like to take some time to describe what that data looks like.
Our dataset spans from 2018 to 2024 and consists of NFL player and team statistics as well as fantasy football draft rankings. This data was collected using a custom-coded web scraper which used Python's Beautiful Soup 4 and requests libraries. We gathered our data from highly reputable sources such as Pro Football Reference, Fantasy Pros, NFL.com, and StatMuse. When it comes to the structure of our data, this has been an ongoing conversation from the time we began this project in 2025, and we're just now getting some clarity. We basically have two options. One being a long format where each row is representative of a player's statistics from a single season, along with their fantasy points scored in the following season, so that would be the target. The other option is a wide format where each row represents a player's statistics for all seasons included. Originally, we planned to go with the wide format to give our model context of the previous seasons. However, after many conversations and much thought, due to the nature of our problem with predicting the next year's fantasy points from this year's statistics, we're choosing the long format. We're already working on incorporating deltas and rolling averages to give our model context. So the statistics for this dataset can be broken into four categories: descriptive stats, offensive stats, defensive stats, and context-based stats. It is worth noting that we have not finalized our context-based statistics, so they will not be included in this presentation. The descriptive stats are highlighted by player name, season, age, the average of our four sources of average draft position, positional average draft position, and our target variables. Walking through our offensive statistics, we see that we have passing stats like yards per completion, passing touchdowns, and interceptions. We also have rushing stats like rushing attempts and rushing touchdowns. Additionally, we have receiving-based stats like targets and receiving touchdowns. And then lastly, we have some statistics that apply to all offensive players, such as fumbles and two-point conversions. When it comes to defensive statistics, we had a difficult time with multicollinearity. So for defensive stats, we have total touchdowns scored, special teams impact, which is the summation of four other variables that were highly collinear, and safeties. On the special teams side of things, we have field goals made and extra points made.
Now we'll talk about our main goals for this project in DSci 592. So we'd like to first and foremost reformat our data from that wide format to our new long format that we talked about previously. We'd like to do some more feature engineering, especially considering the lack of defensive stats and the fact that our initial attempts at modeling have kind of plateaued in terms of performance. And with that modeling, we'd like to produce more concrete player predictions. So we have our PPR, or points per reception, and standard scoring formats. Those are the two main formats for fantasy football leagues. And we'd like to try some linear regression, XGBoost, deep neural network, and MLP regression models, in addition to anything else that we may want to give a shot. Once we feel more confident with those initial modeling steps to produce those predicted player performances in terms of fantasy points, we then move on to our next goal of building an optimized recommender system for drafting players. And that would factor in things like predicted player performance that we just modeled, live draft player availability, and positional needs within the draft. We'd also like to incorporate some custom draft logic that aligns with the best practices in terms of typical fantasy football rules and norms when drafting. And lastly, we'd like to develop a real time draft assistant dashboard that anyone can use, that's customizable, interactive, and very accessible for anybody. Like I said, just a really easy to use and incorporate user interface when you're drafting. And we would like that to support those multiple fantasy scoring formats that we've done our modeling for, so that you can really customize it towards whatever kind of draft you are going through.
So now I'm going to talk about basically how we plan on implementing those goals and how we're going to put it all together. So the first thing that we did is we revisited our data pre-processing ideas, and one of those things was restructuring our data from a wide format to a long format, as Caleb iterated previously. And the main goals from reworking our data was this now enables us to calculate rolling averages, weighting previous seasons in different ways, as well as kind of seeing how a player is performing year over year. And we feel like we have this advantage in a longer format as opposed to before in that wide format. And this is something that we're constantly evolving and seeing how different features are going to impact our modeling. We also reworked another feature, total passing and total receiving, to now yards per attempt and yards per completion. And this will allow our model to capture player efficiency as well as player volume. Before, our total passing and total receiving metrics were very, very inflated, as they just represented attempts times yards. And that was kind of problematic because we had a lot of inflated statistics. And now this will allow the noise in the model to go down compared to what we had prior. So now we look at basically our modeling overview. And our modeling pipeline looks a bit like this, where first we'll scrape the data, we'll pre-process the data, we'll scale the data, then we'll train and test our model, we'll tune our model, and then we'll ultimately evaluate our model. And this process is very fluid, and we often see ourselves, going in a loop, because based on those evaluations, we kind of see, okay, are these evaluations good enough or not? And we'll go back to steps in this pipeline where we kind of tune, maybe change some feature engineering, maybe change some feature scaling before going through this pipeline again and kind of seeing where that takes us. The ultimate goal from these evaluation results is to utilize the output to power a hybrid recommender system to assist players in fantasy drafts. The recommender at its core shouldn't just pick the highest scores or the highest predicting scores. It should reflect draft strategy, because oftentimes what happens in a fantasy draft is the highest scoring players are not taken number one overall due to strategy. And this is because of a lack of depth at other positions. Like, quarterbacks are often the highest scoring players in fantasy football, but oftentimes players will take wide receivers and running backs over quarterbacks early on in the draft. And this comes down to the fact that there are fewer quality wide receivers and running backs compared to quarterbacks. And again, we want our recommender system to kind of reflect some of these strategies in its decision making. So our final implementation of the project is going to be to develop a fantasy draft assistant dashboard. And our goal with this is to design a front-end dashboard to make the model predictions accessible, customizable, and intuitive for users. And we're going to build this with Dash. And we want users to be able to customize model logic, such as the size of the league and the scoring settings of their league, so that they receive output based on their scenario. And we're going to integrate Python libraries to display graphs and visuals, such as Matplotlib, Seaborn, and Plotly, so that users can see why the model is recommending certain players over other players and what goes into those decisions.
In order to evaluate the effectiveness of our model, we ended up using two metrics for the evaluation. The first one we use is the coefficient of determination, or R squared, which looks at the proportion of the variation in the target that we can predict from the features. You can sort of think of it as a goodness of fit, like how well the line actually fits the data. Typically, what you'll see is this goes from 0 to 1, with 1 being a perfect fit where all variation is explained by the features, but it can actually technically be negative in cases where there's an extremely poor fit. We also looked at the root mean squared error, or the RMSE, which is the square root of the average of the squared errors. And we look at this metric because it provides sort of an understanding of the magnitude. So we have both a understanding of the goodness of the fit as well as the magnitude of errors within our data set. For our evaluation scheme, what we plan to do is we plan to use 3 broad splits to allow us to train and test our model properly while also letting us predict for 2025. So we have 3 different splits here. First, we have the train split, in which we'll use to train our initial model. We will also be using cross-validation within our hyperparameter tuning, and we will be using data from 2018 to 2022 with the possibility of expanding it further back years. We also have our test split, in which we will be using to test our model without cross-contaminating the training data, and that will be data from 2023. Finally, we'll use the 2024 data in order to predict the next year's, as 2025's results, and that will be in our predict split. As we just mentioned, we'll also be conducting hyperparameter tuning in order to find the parameters that give us the best results for our models and the highest performance. In order to do this, we'll be using scikit-learn's grid search CV function, which is useful because it lets us automatically tune the combination of the hyperparameters we select, as well as implement a cross-validation regime in order to ensure we have the best practices for results validation. The specific hyperparameters that we'll be tuning will be dependent on the particular model in question, and so it will change from model to model. And once we have implemented this regime and gone through testing, we will select the highest performer to be used as our final model for our data set. And that concludes our presentation. Thank you very much for listening, and we appreciate your time.